which came out clear. So this is fine, but we'll define a metric called rate, which is the length of the original message divided by the length of the code word. So how much redundancy information are we sending compared to the original message that we want to send? And so while we're very robust, it takes many flips for us to get like a completely erroneous message. Our rate is 20%. We need to send those 4 extra bits to get that error correction. So this is where Richard Hamming came up with Hamming codes during his time at Bell Labs. He kind of deduced this over time when he was sending and saving information on devices back in the day. So it basically asks the big question: can we do better, and how much can we do better? And so I can claim that, like, if we want to send an 11-bit message, we can correct 1 error and detect 2 errors using only 5 extra bits to make nice blocks of 16 bits, right? Because we like powers of 2 when working with integers and things in our machine word, like models of computation, like our computers and ramps and things like that. And so, we can consider the rate again, and we get to a 68.75% rate, which is much better. We're only, incurring a very small overhead for that level of error correction. So we're gonna kind of look at this as blocks. So I'm gonna look at this just 4x4 block, and you're gonna see in a bit how this generalizes to any size block, but 4x4 is easy to have on a slide. So we're gonna consider a 16-bit block, all right? And we want to fill it with a message. And for right now, I'm just gonna use the 11 lower bits and reserve this top corner. You'll see why in a second. So I have this message 01101001011. I fill out my block, and now I'm gonna use the 5 bits I didn't touch as parity information. So this will mark certain regions of parity, certain regions of the block to maintain the parity. So if there's an odd number of bits in a certain region, we'll set that parity bit to 1 so that it stays even. And if there's an even number of bits in the region that we're considering, we're going to set that bit to 0. You might be wondering, why not just track the parity of the whole block? It's surprisingly more effective to track parities of reduced regions, because then you can start asking a series of questions of where that error is instead of whether or not there is an error. So this first bit, we're just going to consider the data bits within these 2 columns. All right. So when you're doing this in implementation, you kind of compute what each of these parity bits should be ahead of time, and then you set those bits later. So even though these highlighted regions might cover over parity regions later, we're gonna kind of just ignore them. It does work out at the end of the day. Even when you set all the parity bits, those regions will still show the correct parity. The next bit does the other 2 columns, and then we'll use this bit to do these 2 rows, and then this bit to do these top 2 rows. So for this specific message, we actually need to set all 4 of those bits to 1 to maintain the parity of all 4 of those regions. And so now you might notice that this 0th bit position we kind of ignored. We didn't really need it to cover all of those columns and regions, but we can still put it to work. We'll set it to 0 to keep the entire parity of the table. So this is like a second stage if you were to implement it. What this lets us do is, if there's some error that happens in this table, we're able to locate it and correct it. We'll go over that in a second. But if 2 errors happen, then we won't be able to correct the second error, but this overall parity bit will let us know that it has happened. So we can reject the block if we know it's too bad. So now what happens is, if we have flipped one of the bits, we can ask 4 questions. And those 4 questions are, does the parity bit match the region it's associated to? So this bit no longer matches the region it's associated to. We have 5 bits that are marked in these regions and that parity bit is marked as 1 when it should be marked as 0. So this question tells us that the erroneous bit is in one of these two regions. And then when we ask this question, all right, we know that the erroneous bit is in one of these two regions. And from there we can work out, using these series of questions, checking each of these bits and making sure the regions are all same, we can actually find and correct that error. So that's how this simple Hamming code scheme allows us to correct one error. And then if there was a second error, we can check this final last bit. So with that, that's kind of like the high level overview of like Hamming codes again. Are there any questions? Yes. You have the no yeah, so you go to the intersection and you know that if this bit is maintaining the incorrect parity, one of these two is wrong. So you know that if this bit is maintaining parity as well, you can tell that a message bit was wrong instead of a parity bit was wrong. So you take the intersection of all these questions and then you can tell as like one final sanity check whether or not the parity or the message bit was wrong. And it works out either way. If the parity bit was wrong, the same like 4-question scheme still ends up working out. All it's doing is just maintaining, effectively it's like taking the XOR of all the bits that we want to keep track of. So it's 0 when all the bits are, when the number of ones are even, and it's 1 when the number of bits are odd, so that the total number of bits, including the parity bit, is always even.
So how would you know that the error is in that, like, I guess 3 over 2 down instead of 3 over 4 down? Like, couldn't it potentially be that
so
that should have been 0 instead of 1?
This parity bit tells me that it's in one of these two columns, right?
Yeah.
This check tells me that it's in these two rows,
Yeah.
but these checks told me that it was not in these other cells. So I eliminated them from the other checks.
Yeah, so it's not, the error is not in any of the red boxes on the left or on the far right.
Yes, but even those intersect the rows as well. So we know that it's not in these two locations, which eliminated these two as well.
Yeah.
From here. So we're just left with the one cell after asking all 4 questions.
I'm talking about the cell on the bottom row and the third column. That one.
So this gives us the potential that it's here.
Yeah, that's right.
Did I screw up? Did I screw up? Oh, I don't think so. Why am I blanking on this? Oh no. Hold on. New section. Bits. Get back to you. I'm kind of messing this up in my head, and I didn't. It's on me for not like running through the calculations. In practice, this is actually like a Python one-liner.
Okay.
I don't think I actually.
Don't go back. You don't have to go.
I don't think.
Yeah, seems like there's 4 that it could be.
I might have made a mistake in how I drew this. I'll get back to you. In general, you know, you're asking these series of questions and you end up eliminating half of the options each time. Over 4 questions, you are able to get down to 1 of them. Because you are like you're 2 to the 4, right? So, you know, we're 2 to the 4, 16 bits, so 4 questions will eliminate half the options each time until they get down to 1. I think I'm missing 1 final step. In practice, you can actually check this error if you have the sequence of bits that you got. If you repeatedly XOR each of the numbers in like a rolling XOR, it will tell you the position that's wrong. So this might be bad on me. Okay. In general, though, what we've described is a 1511 extended Hamming code. So we supply 11 bits of message. We have that 4 bits of error correction parity. And normally you could just send that, but because, you know, we like things in practice, we have that extra 1 bit that gives us an extra layer of detection. And so you can expand it to any table size. You can say to the n-1 code for, you know, your block size, and you're able to send a message to the n-1. And so you end up placing each parity bit in the row and column corresponding to powers of 2. So, you know, in this case, this is position, you might consider this like position 1 and position 2. If this was, you know, double the table size, we put the next one at position 4, and then the next one at position 8, and the next one at position 16. And that's how you can like expand these tables out and get the same like cutting property when you do extended Hamming codes. So in a 2 to the n block, we can efficiently detect 2 errors and correct 1 error. And that's what the extended Hamming code gives us. So in practice, you can implement Hamming code processing in hardware. This is what your RAM does when it copies and pastes, you know, memory from place to place. It's usually implemented in hardware. You never have to work with it. C never has it come up. But you run into this issue where when you do send info, errors tend to happen in bursts, right? So like at some point, you know, the transmission goes down for a period of time. So all those sequence of bits get flipped or zeroed out or whatever it would be. And so if we have like this very low resilience to number flips, that's bad. So we end up interleaving the blocks, because if you do have this period of downtime, then you take on all those errors across multiple blocks of information. And so you're able to correct every block of information efficiently. You don't have to worry about it. So this brings us to our next section, which is talking about the Hamming bound. So there's a couple of good ways of talking about how these error correcting codes help us bring down the space of bad codes. So it's a metric of how efficient can we get with error correcting codes, because at some point, if you consider the space of all the possible messages that you can make with some, you know, length string, you're going to consider some of those correct and some of those incorrect. And the idea of an error correcting code is that it will cover all of the incorrect strings around your correct string, so that if you do get an incorrect string, you can somehow retrieve it and walk back to your correct string. So we can get a lower bound on how well these error correcting codes can cover these invalid steps, these invalid flips, with the Hamming bound. And it gives us the efficiency of how well any corrector code can utilize that space within a code. And codes that achieve this bound exactly are called perfect codes, which is an interesting name, but you know, they're called perfect codes, even though that this bound is, I think, a loose upper bound. It's not tight. So it's quite actually difficult to compute the exact bound that this is, you know, measuring. So this is a lot of math, but effectively, we're considering this number of possible codes to be bounded by this fraction. And so we consider the Hamming distance D, which is the number of flips it takes to go from one string to another. So in 3 flips, I can go from some binary string, regardless of where those 3 flips are, to another. So I would say that those 2 strings are of Hamming distance 3. And so we consider, a code of length n, and we get this of our language size raised to the n. So like our language is a binary, so this would be 2 to the n. And then this sum over binomials, which we'll talk about here. So we're effectively considering, we're effectively considering that over all strings of length n. So we're considering, the size of sigma raised to, so in our case, 2 to the n. We can make at most t, which is the Hamming distance minus 1 divided by 2 errors. And this is, consistent with what you saw. If you are able to cover enough Hamming distance, then some fraction of that you're able to correct. Once you know how many flips it takes to go somewhere, like past that, that which direction you came from. That's kind of the idea that that's going for. So we can make at most, d minus 1 divided by 2 errors. Then our code C covers the sum of all errors k up to t, choosing some k bits to flip to the other bit. So if I replace everything with our binary language, we're saying over all strings, if I take so many errors, I choose some of those bits in the string to flip. And as long as my Hamming code can cover that many strings, it's considered perfect. Because that means with that code word, I can recover my errors. And then a different code word covers all the other possible strings for that Hamming distance, right? Because at some point, if you make enough flips, you're at another valid word. So I can't distinguish what was so erroneous that I ended up to some other word, right? If I replace the string hello world with like hi mom, like eventually, like I made so many flips in the string that I got another valid message. I can't tell without some other like overarching structure that like the original message should have been, hello world. It's just like at some point you're gonna run into another valid string. But it is a perfect code. You're saying that within the like movement of flips between a valid string to an invalid string, I can detect that and cover that. So we have a query language where we consider some string of length n. How many strings can we make with at most d changes and consider within our code word? So our basic 1511 Hamming code, we're ignoring that 0 overall parity bit, requires 3 flips to go from one valid code to another. It's you might be like, can I do some like aggressive 3 flipping? Maybe, but in most cases, 3 flips you'll change it in such a way where all the parity bits are okay, even though it's not your original message that you intended. So we can detect errors at 2 flips or less, but once we go above 2, we can't distinguish between valid messages. So we would say that our Hamming code can represent with a minimum Hamming distance of 3, where our message length is 11, so we cover 2048 strings within a Hamming distance of 3. Right? So we cover all those strings, we're able to detect and correct errors within a Hamming distance of 3, so 2 or less. And so we say this is a valid, code for 2048 possible strings. And if we compute this Hamming bound for 15.3, we get, 2 to the 15, this 2 minus 1 drops out, and we're just doing this choose 15 over k for 0 to 1, so 1 plus 15 is 16. We get 2 to the 15 over 16, which is 2 to the 4, we get 2 to the 11, which is 2048. So our 1511 Hamming code matches the Hamming bound. So it is a perfect code. But we talked about that extended Hamming code, where we use that 0th bit to detect one more error overall. So we're able to detect 2 errors of current error. So that means we're making 16-bit code words, and we have a minimum Hamming distance of 4. Well, if we compute, our bound for 16,4, we get 3855.06, which is a very reasonable number to consider when we're talking about discrete binary strings. but we didn't change our message length. We can still only represent 2048 word strings, but we're just more robust in doing it. But, you know, it's not a perfect code. Extended Hamming codes are not perfect, but in practice, they're a lot easier to implement because chaining 15-bit codes in, you know, a memory words where we like 16, 32, 64-bit integers and words and things like that. It's you're just wasting more compute power to like try and shift things around. You know, nice power to two are easy to send around. And so that kind of wraps up this idea about Hamming bounds and Hamming codes. And we'll get back to you on how I screwed that up. That is my bad. There's a lot of neat things I want to get into, but kind of gets into like a really abstract things about sphere packing and geometry. Sorry, but when I talked about like covering valid messages, right? You can actually represent this as a metric ball in some space, and so there's this really interesting dynamic between Hamming codes and sphere packing, which is like, how did my error correction information lesson become a geometry lesson? But it's not super easy to display without really nice pictures, and I would need like a month to draw nice pictures. But yeah, so Richard Hamming actually got his PhD here. I don't know if that was a known fact prior, but yeah, he graduated with his PhD here a long time ago. He got his Nobel Prize for this type of stuff back in the 1960s. All right. Any final questions? Okay.